Okay, so we have these bags of chocolate chips. There's some suspicion that this machine is underfilling so that the average weight of a bag is less than the 441 that it should be. And so we're conducting a test to figure this out. So let's draw a picture of what's going on here. And when we draw this distribution, we're assuming it's normal, by the way. We're drawing the distribution of sample means, and the average of that distribution is going to be the same as the null hypothesis mean. So this 441 grams. If nothing's going on, if the bags are being filled exactly to the weight they should be, then the average of those samples of size 26 should be 441. The standard deviation of this distribution would be the population standard distribution. So let me get that really quickly. So we have S squared equals 900, which means that S itself, the standard deviation, should be 30. That's the sample standard deviation. We don't know what sigma is. We don't know what the population standard deviation is. So the distribution of sample means, in other words, if we would take a 26 bag sample, get the mean, take a 26 bag sample, get the mean, and so on. If nothing was going on, if the machine really was working as intended, then it should be this 30 divided by the square root of n, square root of 26. So that would be the standard deviation here. We're looking at a sample mean of 433, so that's somewhere over here. Wow, that was a horrible 3. My apologies. We're looking at that 433 here. Now we don't know quite how far it is yet. We could use that standard deviation, this divided by square root of n, if we wanted to draw it better, but for now let's just leave it like this. And now let's go ahead and get our t-test statistics. So let's figure out where our sample actually weighs in on things here. T equals, and so we're using the formula from chapter 10 where we have the sample mean minus the null hypothesis mean over sample standard deviation divided by square root of sample size. So let me go ahead and fill those in. Okay, and 433 was our sample mean, 441 is our null hypothesis mean, 30. Do make sure that you're using sample standard deviation, not the variance, and square root of 26. If you don't get negative 1.36 when you're doing that on your calculator, probably it's happening right here. If you would just do this minus this divided by 30 and then divided by square root of 26, it's possible you could run into some problems. So make sure you're dividing by and then putting a parentheses around this part. And if you don't know how to do that, you could always do this separately first, write the approximation, and then type out the numerator and divide. So the question is, what do we do with this t equals negative 1.36? How does that help us find the p-value? Well, the p-value here is the portion that's shaded right here. We are doing a left-tailed test because it said the alternative hypothesis is that we're underfilling the bags. In other words, that we're less than the null hypothesis mean. So it's a one-tailed, it's a left-tailed test. And we know that if this area is more than 0.02, we would fail to reject the null. If this area was less than 0.02, we would reject the null. But how do we get a p-value out of this t equals negative 1.36? Well, one other thing I want to point out is that our sample size is 26. So keep that in mind. That means our degrees of freedom for a one sample test like this is going to be 26 minus 1, be 25. Now when we get into two sample t-tests where we have two entirely different samples, two sample standard deviations, and so on, we're going to have to subtract 2 to get our degrees of freedom. But here we just subtract 1 from the sample size. Okay, so how do we use this information of 25 and negative 1.36 on the tables? We do want to go to a t-table, and let's do area in one tail because we're talking about this left-tailed test here. And we know that our degrees of freedom is 25. So the tricky part here is that negative 1.36 is somewhere in between these two values, right? And we're talking about the area and the tail, so that's why they don't have a negative. Just think of 1.36. But 1.36 at 25 degrees of freedom is somewhere in between these. So we know our p-value is somewhere between 0.05 and 0.1. And if we come out to how they want us to give the answer, it says you may write the p-value as a range using interval notation or as a decimal value rounded to 4 places. In order to get that decimal value rounded to 4 places, we're going to have some kind of technology, whether that's a SPSS or an Excel spreadsheet or your calculator. By using the tables, the best we're going to get is this interval notation. So like we said, we know it's somewhere between that 1.36 gives us somewhere between 0.05 and 0.1. So we can put 0.05 and 0.10. It's somewhere in between there, and that would give us a correct answer. And so that's all it asks us for here. If it had asked us what our decision is, we would have needed to get below 0.02 in order to reject the null. And our p-value, even though we didn't get it exactly, we know it's somewhere between 0.05 and 0.10. So if we had to make that decision, we could say that we're going to fail to reject the null because anywhere in that range is above 0.02. It's definitely not going to be below 0.02 there. Even if we use the technology, it should tell us a value that's somewhere in between these two. So failing to reject the null means that we weren't able to get convincing evidence that these machines are underfilling the bags of chocolate chips.